Now we are going to talk about another class of games, and it's a bit orthogonal in its sense to potential games, and that is zero sum or constant sum games. Actually, we're going to talk about the constant sum games. So, uh, when we talk about constant sum games, we talk about games where we have two players with opposite goals. It's orthogonal to potential games in the sense that in the potential games there is a common measure. The potential is a common measure. Well, here we have opposite goals, and they're also called sometimes strictly competitive. And that is probably one of the, if not the first class of games which was studied as as a part of game theory, not just economics, but game theory, the abstract study of interaction, by von Neumann and Morgenstern. So I think they were those who originated that study. And for these games, we have a very beautiful theory. Of course, we know that we don't have it for the general games. So that is a win-lose situation. Like chess, football, many other sports, you have this that what the one gets is exactly what the other one loses. So if I win, you lose. If you win, I lose. If there is a draw, it's also common. So we, I get a draw, you get a draw. So we both get like half, or one of us gets all the victory. So exactly this idea of I get what you lose. Also, when we divide some given value, divide in a pie, what that's how it's usually called. That's also an example of zero-sum game because the pie is given. So let us go over those games. The agenda is now we're going to study constant sum games. So the sum is constant, not necessarily zero. It's pretty much the same as the sum is zero, and often people study only zero-sum games. So it's simply a bit more elaborate technically. So you can feel a bit better that we're studying a bit more elaborate version of that. But it's pretty much the same as zero-sum games. So you just have this constant you need to move around sometimes. And in the case of zero-sum games, that constant is zero. Then we're going to define Maxmin and minmax, which can also be defined for other games. Basically, when you maximize what you can get, given that the other person is minimizing what he can give you, or min-max the other way around, that you minimize the other person's value, given that the other person maximizes it. But those values have meaning, a very special meaning in the case of zero-sum games, and that will allow us to characterize Nash equilibria of those games. You see, I wanted to say constant sum games. So whenever I say zero-sum games, it's probably constant sum games. It's probably a tongue slip. And the last thing, we're going also to discuss the notion of a value of a game. So first, the definition is as follows. A game of two players is called constant sum if there is a constant such that for every profile, the sum of two utilities is this constant, C. And zero sum means that this constant is zero. And as I said, it can be also studied for zero sum because having an arbitrary constant does not change anything. I mean, it does change by this constant, but not really something substantial. And the intuition is that the interests are exactly opposite. Of course, there are games, by the way, where the interests are neither opposite nor uh, aligned. So it can be a game which is neither potential nor zero sum. Now, let us look at some examples of zero sum games. So, first of all, our old friend matching pennies. So it's either matched or not. And in both cases, the sum is one. So one person wins and exactly one person loses. In this case, there is no Nash equilibrium, as we know. Another example is a game like chess, for example. So in chess, there are many strategies for each player because the strategy tells what to do in each position. So it's really, really complicated. And actually, it can be even even that what to do depends on how we got into the position, because sometimes in chess there are rules which depend on the past, like, so the position needs to depend on the past, shall I say, because you can exchange the king and the tower only if you have not done that, and only if the king has not moved. So there are rules which actually tell you that it's not only the position on the board which is important, but also how we have gotten to the current board position. So the path in the tree of the game is important. Anyhow, there are many, many strategies, but anyhow, the utilities are 1 minus 1, so when the whites win, minus 1 1 when the blacks win. I imagine here, I assume here zeros, the player 0 is white and player 1 is black. Or 0 0, that's when they have a draw. Here, actually, it can be proved that there exists an equilibrium. We don't know which, but we can prove that it exists, and we will prove this later in this course. Now, another interesting game, which is zero-sum, is the famous rock, paper, scissors game, which also does not, also like the pennies, matching pennies, does not have an equilibrium. And this game is, yeah, it's quite a famous game. So that when you have two actions which are the same, let's say rock, rock, paper, paper, or scissors, scissors, then it's a draw. But if it's different, then rock can be covered by paper, so it loses to paper. But scissors get blunt when they try to cut rock, so scissors lose to rock. And they cut paper. So there are those words which describe, and there are those numbers which describe the game. And as I said, there is no equilibrium in this game either. And now let's look at a similar, at a simple stylized but a very interesting, realistic example. So very simple, which is called bipartisan election. So the players are the two parties, and they want to get as many parliament seats as possible. Since the number of the seats is capital P, it's a zero-sum game. And it holds for any division of a given asset. Now, a concrete example is that you have a two-dimensional given distributions of the voters, and there is a density function of the voters, which we, let's say, know, which describes what is the distribution. The players, those parties, choose at which position on the given line they stand. So which stance they take between A and B, say between 0 and 1, whatever. And the utilities are defined as follows. So if one of them is smaller than the other one on this line, then the utility of the smaller player is the total number of those who are close, the total mass, probabilistic mass, not probabilistic, but the total density. So it's the total number of voters who are closer to Si than to Sj, which is simply the integral between the left boundary till the middle of those two players. And what the other player does get is the number of those who are closer to him, which is the integral between the average between Si and Sj and the right border of this segment of the density function. Now, if both Si's S1 and 2 are equal, simply then you integrate all the voters and you just divide their votes between them. Because in this case, they don't share, don't have own consistent own constituency each, but they just share the same players because they're at the same position. So what do you think? Is there an Nash equilibrium here? It's clear that it's a zero-sum game because the sum is always the total integral between A and B. But is there an equilibrium here? Yes. And the only equilibrium is when both players position themselves at exactly the same place, such that the integral from the left border to that place is equal to the integral from that place to the right border. Now there is such a place because an integral as a function of its border is continuous, so it gets any value. There is such a place. And let's say if the voters are distributed uniformly, it means that they both have to be in the middle of the segment A and B, and otherwise they adjust in a way which equally divides the voters to the left, those who are to the left and to the right. Now, let us prove now why this is the only equilibrium. Now, first of all, if the values are not equal, let's say is I strictly smaller than Sj, then it's not an equilibrium because I will profit strictly by becoming closer to Sj, because then it will get more from from those who used to be between them, because now it gets closer to Sj. Therefore, in any equilibrium, they have to be at the same point. Now, if they're at the same point, but the integral of f between A and that point is smaller than the integral between that point and B, it's the same, of course, if it's bigger. Let's just assume that it's smaller, and then we see that it's not an equilibrium. Then any player can move a little bit to the right, such that the integral to the left from A to Si plus epsilon is going to be still a bit smaller than the integral from Si plus epsilon to the right border. But then that player is going to single-handedly get all that it has at the to the right. It also is going to have something between those players, but it's definitely going to get all the integral from Si plus epsilon to the right border, which is more than the other part of the integral, which is better than half of the whole integral, which it used to get before, because they are at the same point. They were at the same point. So it can get more than a half, and that's a profitable deviation. So we have now proven that the players have to stay at the same point, and the integral from A to that point has to be equal to the integral from that point to B. And now we have to prove that if that is the case, if S1 is equal to S2 and they are both at this set where the integral actually I need to assume that f is strictly positive. If let's say that I said that in the beginning that if I move a bit and I will strictly profit, I need to assume that f is strictly positive. Okay, so I'll assume that f is strictly positive. see. I can assume. I can even assume. Uh, so it's and let's say continuous. I think it's more than I need, but I just want to have this property that the integral of f on any non-zero segment is strictly positive. Yes. Okay. So let us get back to what we said. So, uh, and of course, then the set of all those points x such that the integral from a to x is equal to the integral from x to b includes exactly one point, because the integral is from a to x as of fx dx is then a strictly increasing function. But okay, so what we say now is that if s1 is equals to s2 is indeed such that the integral from a to that point is equal to the integral from that point to b, then any deviation, let's say that some that I wants to go to the left of Si, then I will get the integral from a to the point in the middle between Si prime and Si and Sj. So to the point Si prime plus Sj divided by 2. Now that's strictly smaller and definitely not more than the integral from a to Si prime, Si, because Si prime is to the left of Si, and therefore so is the average of Si prime and Sj. So therefore the player will not profit, and that's a proof that deviation cannot improve what the player has. Of course, the same goes if the player deviates to the right. Therefore, it's energy equilibrium. So we have proven that that's the only energy equilibrium. And actually, there were elections. I don't remember exactly which. I think it was somewhere in Latin America. It was not about the number of seats in the parliament. It was simply about winning or losing. But the elections had, I think, 2 rounds, and before the second round, both candidates tried to move to the center. Exactly, they wanted to be kind of closer to the median vote. So this behavior does take place in real elections. Okay, having shown some examples of zero-sum game, let us get the nice properties of those games. So first we need to define the maxmin and minmax. And the definition is simple. We just need to think, what does it mean? It means that the best possible what I can do, assuming that the other player wants to hurt me as much, that's the maxmin. I maximize, giving that the other player minimizes. It's relevant because hurting me is benefiting him. That's a constant sum. And it's relevant. Now it basically shows what is the maximum path I can guarantee, even if the other player wants to hurt me as much as possible. And this will also characterize, help us characterize, as we will see, Nash equilibrium. So X star of S1 is max minimum for that player if the utility that it gives to player 1 is the best possible utility against the worst possible Y. So if you choose the worst possible Y, the best thing for you, for player 1, is to choose X prime, X star. So X star is a maximum over minimum of Y in S2. Analogously, uh, analogously, Y star is a max minimizer for player 2 if it gives the best utility of that player among all the other Ys when the player 1 wants to make the life of player 2 as bad as possible. So it's maximum over minimum for U2. Okay, that's the definition of max min and min max. And first, no, it's only max min. Max min. Both players want to max min. Now we are going to prove a connection between max min and min max. And that is as follows.